Hi everyone, in this video we look at the strange idea of wave-particle duality, which is a fundamental idea of quantum physics. It is difficult, so you will need to work hard to fully understand all the concepts. I hope you enjoy the video. This is the third video in the quantum physics series of lessons. So this will cover electron diffraction, wave-particle duality, we'll look at the de Broglie or de Broglie equation, and we'll look at some exam questions as well. Right, so what do we mean by wave-particle duality? So earlier on in this course, we've looked at the Young's fringes experiment, where laser light was diffracted and then we had interference. So the Young's fringe experiment is strong evidence for the wave behavior of light, and that is one of the significances of the experiment. Earlier on in this series of videos, we looked at the gold leaf electroscope, which is the photoelectric effect, and we said this was strong evidence for the particle behavior of light. So we've got two distinct models, wave behavior, particle behavior. And normally we assume a lot of particles in physics, for example electrons, behave as particles because they have a mass, they have a charge, they have a velocity and a position. So we would normally assume that electrons behave as particles. So this takes us into the electron diffraction experiment. So this is a really important thing that you need to be able to describe in the exam. So we've got an electron gun where we produce a beam of electrons. So we don't need to understand this process, but it's due to a heating, something called thermionic emission. So we produce a beam of electrons and they're attracted towards positive electrode, the anode, and then targeted at a target. So usually carbon or graphene, and then we get this circular pattern. So what's happening is we're getting diffraction, so that's what waves do, and then we're also getting interference. So we've seen this in the waves topic, we're getting constructive and destructive interference. So this is really, really strange because the electrons are behaving as particles at the start and at the end when they interact with the phosphor screen, but in the middle they're behaving as waves because we're getting diffraction and interference. So this strange behavior of particles and waves is called wave-particle duality. So we've seen already that light waves can behave as particles with the photoelectric effect, and electrons can behave as waves, which is very, very odd. So this is a key aspect of quantum physics. So on a very small scale, we cannot predict with certainty where a particle actually is. And trying to visualize this is very, very difficult. So we could imagine a wave of particles or particulate waves, but neither of those is quite right. It's actually a probability wave. And when we look for the electron, then the probability wave collapses and we have a likelihood that the electron will be in a particular place. It's a very, very counterintuitive idea. So we need to make sense of this and understand which model to use in a particular circumstance. So these are some guidelines here. So if the light is interacting with matter, that is the photoelectric effect, then we use the particle model. If the wavelength of light is similar to the dimensions of the object, we use the wave model, and we saw that in the wave topic. That's when we get the most diffraction. If matter interacts with matter, then it's a particle. Well, that makes sense. That's a transfer of momentum, and that's Newtonian forces. So this final point is really key. If the wavelength of the matter is similar to the dimensions of the object, then we use the wave model. But that begs the question, well, what is the wavelength of a particle? So we need a new formula, and this is the one that we use. This is the de Broglie formula, or the de Broglie formula. And sometimes this is referred to as the wave-particle duality equation because we have the Planck constant, that's the constant of proportionality. We have lambda, the wavelength, which is obviously a wave property, and on the bottom we have m times v. Mass and velocity, m times v is momentum. So this is combining particle properties and wave properties. So let's have a look at a few examples using the de Broglie formula. So there's a few questions here. If you want to pause the video and try these yourself, that might be a good idea. So this first one we've got, it says find the wavelength of an electron moving at a particular speed. So we know the Planck constant, we're given that, and we know the mass of an electron, we're given these in the formula booklet. So if we put these into the de Broglie formula, we get Planck divided by the momentum, and we get this value here, 7.3 10 to the minus 11. What we need to do then is compare that to the gap that we're passing through. So we've got a wavelength of 7.3 10 to the minus 11. The lattice spacing, that's the gap in this particular case, is 8 10 to the minus 11. So they're both 10 to the minus 11, that's the same order of magnitude. So we would say that we do get diffraction, and therefore in this instance, this beam of electrons is going to behave as a wave. So we could do this for some other examples. So if we have a neutron beam, well, that's the mass of a neutron moving at this speed, same as before, and a slightly different gap. The first thing we do is to calculate the de Broglie wavelength, and we've got Planck constant divided by mv. This will give us 3.68 10 to the minus 13. So then if we compare that to the gap, 8 10 to the minus 10, so we're a factor of approximately 1,000 out. This is much, much smaller. So this beam of particles is just going to pass straight through the gap. We won't get any diffraction. It won't behave as a wave. It's going to behave as particles. We can also apply this to any situation. So rather than just at a very small or quantum level, we can consider cars and planes and people, and we can work out their de Broglie wavelength. So for example, if we have a person with this mass and this speed here running at a doorway or running through a doorway, a gap of 0.8 meters wide, we can ask the question, do they behave as a wave or a particle? So the first thing we need to do is to calculate the de Broglie wavelength. And not surprisingly, because we have a fairly large mass and velocity, and Planck constant is very, very small, then we get this tiny, tiny wavelength, 10 to the minus 36. So this is so small as to be totally negligible in our day-to-day life. We cannot see this in any way or really measure it, but we can calculate the wavelength. And then we can compare that to the doorway gap of 0.8 meters. So similar to the previous one, there is a wavelength, but it's so tiny that it's not going to have an effect here. So fortunately, people in this case are going to behave as a particle rather than a wave, which is great, because if you diffracted into a room, that would be a little bit socially embarrassing and possibly a bit unhygienic. Right, let's have a look at some questions. So this first question, really important, very, very typical question in the exam, longer response question. Name an experiment which demonstrates that electrons have wave properties and describe the main features. So that's definitely something that we need to know for the exam. Question 2 is a fairly straightforward de Broglie calculation. Question 3, a little bit more difficult, but again, fairly standard. Question 4, I would say, is the grade A star question. So as always, pause the video, give yourself 20 minutes, half an hour to work through these, and then check the answers when you're ready. Question 1, so this is a really important question you need for the exam. The name of it is the electron diffraction experiment. What's happening? Electrons are fired at a crystal or at a target. We could make reference to the de Broglie formula. The wavelength of the electrons is a similar size to the gap between the atoms. So diffraction takes place. What do we observe? We get this circular pattern on the screen, which is a fringe pattern, which shows constructive and destructive interference, which demonstrates that particles behave as waves. So exam tip, include lots of detail. Always useful to make reference to a formula and use the correct terminology. And this is a bit of a synoptic type question because we're referring back to the work we did in waves, so fringe pattern, constructive, destructive interference, wavelength, and so on. We say question 2 would be a fairly straightforward question in the exam. You might get something that's simple, but all we need to do is to select the correct formula and substitute the values, and we get the wavelength. In this case, it's going to be 1.21, 10 to the minus 10. And then we need to compare that to the spacing, same order of magnitudes, 10 to the minus 10. So we're going to have wave behavior, we will get diffraction and possibly interference. Perhaps not surprisingly with the football. So again, we can calculate the wavelength. We've got a relatively large mass and large velocity, well, a relatively small velocity. But because we have this dominant Planck constant on the top, then we're going to get this very, very small wavelength. If we compare the wavelength to the gap, 0.8 meters, then it's much, much smaller, so no diffraction takes place, and the football behaves as a particle. So a couple of points on this for exam tips. Always show your working, very, very important. Always make sure that you make a comment if required. So it says decide whether a wave or particle model should be applied. A typical lost mark in the exam would be students just calculating the wavelength and then not saying whether it's going to be a wave or a particle model. So make sure you answer the question and get that extra detail in. Okay, question 3, so a little bit more difficult. So I've given you the hints here. You wouldn't get those in the exam, obviously. And again, this is a bit synoptic because it's referring back to the work in the electricity topic. So we've got 5 kilovolts, 5,000 volts. What is the energy of each electron? So we're assuming that they're stationary to start with. They're accelerated through this PD of 5,000 volts. We can calculate the work done on the electrons, which will appear as the kinetic energy. So work done is Q times V. We know this from the electricity topic and also from the formula booklet. So all we need to do is to multiply the charge of one electron by the voltage, and we get the energy. So this is going to be the energy gained, which will appear as kinetic energy. And again, you wouldn't get this hint in the exam, but we do need to know that the work done is when we have an energy transfer if a force moves a distance. So we have a transfer from electric potential energy into kinetic energy. So mathematically, fairly straightforward. Rearrange to make V the subject, use your previous value, and we've got the mass of the electron, and we can find the velocity. Expect a really high value, so 10 to the 7 sounds about right. If you're getting much lower values, then you've probably made a mistake, because normally electrons move extremely quickly. What is the wavelength? So we're going to use de Broglie. So we can put the numbers into the de Broglie formula, and we get 10 to the minus 11. And we might anticipate it's going to ask us about, does it behave as a wave or a particle? We know it's going to behave as a wave. Oh, it does, there we go, part D. So it says, what would happen if they were diffracted, or so if they were directed at a gap of 10 to the minus 11. So it's the same order as the wavelength. So the electrons will behave as waves, they will diffract and interfere, which is what we'd expect to see in this case. Exam tip for this question, always show your working, especially on multiple stage calculations, because if you make a mistake right at the start, you're going to carry that through all the way, and you will get error carried forward even for incorrect answers, only if you show your comprehensive working out. Right, more difficult questions. So if we increase the voltage, so perhaps not surprisingly, we're going to get a larger energy, a larger kinetic energy, which will appear as a larger velocity. And then we link it to the de Broglie formula. A larger velocity, we're divided by a bigger number, but the mass hasn't changed, h hasn't changed, so lambda is going to be a lower value. So then we need to think, okay, if it's a lower wavelength, how will that affect the fringe spacing? And we can make reference to the Young's fringe formula here. So we've got lambda is equal to A times Y over D, and make Y the subject, Y is the fringe separation, is equal to lambda D over A. So the distance hasn't changed, the slit spacing or the gap hasn't changed. If we have a lower wavelength, then we're going to have a lower fringe spacing. So quite a difficult question, quite synoptic. It's bringing together lots of ideas, and in your answer, you would need to make reference to the formula. Finally, we've got why do we get circular fringes rather than a line, which is what you might expect, for example, with the Young's fringes or the diffraction grating. So this is a little bit more difficult, and the exam tip here would be to read around the subject, read your textbook, try some extension questions, look at the more complex questions whenever you get an opportunity, for example, with the Physics Olympiad, because this is a little bit more difficult. And to explain it, we need to think, well, what's going on just if we have two slits next to each other? So if we have two slits, we get a line of fringes because we only have one plane, one orientation of slits. But actually the way the carbon target is structured, so graphene consists of multiple layers of gaps, all at different orientations. So not just 4, but thousands and thousands of orientations. So we might have a horizontal orientation and a vertical, and then at another angle. So wherever we get these particular orientations of planes, we're going to get effectively a line of fringe spacing at that particular angle. So if we have multiple different planes at all the angles all the way around a circle, 360 degrees, we're going to superimpose these lines on top of each other, which will create effectively a circular pattern. Right, well done, everyone. You've made it through what I think is a really interesting but very difficult part of quantum physics. I recommend you have a look at the next lesson in this series, which looks at emission spectra and absorption spectra and energy levels. Great, see you next time. Bye.